Welcome back, students. Today we are going to start a next unit on artificial intelligence, that is fourth unit. So in this unit, what we were going to discuss today is on the basics on Markov decision process. So as you are already aware, what is a Markov process? And using that Markov process, we have seen a model called hidden Markov model. So today we are going to see that how this Markov decision process can be formulated. So before that, we need to understand what is meant by reinforcement learning. So this reinforcement learning is actually a part of machine learning. So you know, machine learning contains three types of methods such as supervised learning, unsupervised learning, and the next is reinforcement learning. So here the reinforcement learning is one of the type of machine learning. What is actually performed is that, you know, what is mean by machine learning, like learning from the given inputs. I mean, based on the situation, it adopts the things and it performs accordingly. So here what happens is that reinforcement learning allows machines or software agents, which we have already discussed in unit 1 regarding agents concept, right? So that agents are machines, whatever we are implementing, so it automatically determines the ideal behavior, okay, how we are going to perform. The intention is to maximize the performance. So if a performance has to maximize, what kind of strategy will be followed by reinforcement learning? The strategy is simple, that is called as simple reward feedback system. I mean, you can simply call as feedback system. So using this simple reward feedback system is being adopted in reinforcement learning. What do you mean by feedback? For example, one agent is there, it is presently in one state, and as if the agent moves from one state to another state, so what happens? A reward will be awarded for that agent. So that reward can be positive, can be negative. It depends on the step what the agent has been adopted. So using that reward, we can calculate that how efficiently the agent is performing. The purpose of reinforcement learning at the end is that you need to maximize the reward, okay, to reach the goal state. So that is how we are going to learn here. So because of that, in Markov decision process, actually this is one kind of problem which is adopted in reinforcement learning, and we need to see that how a matter of fact, I mean, like if I'm using an agent in an environment with the help of environment, and it performs certain set of actions, so that actions has to be performed by that agent. So this Markov decision process is actually a problem, okay, that will be adopted here, so in reinforcement learning. So if you see classically, like how this reinforcement learning cycle performs is, I said you that one agent is there, okay, this agent I just said you it can be a software program. If you take a robot, something you can call to be as an agent there. So what happens is that an agent is there in one state, okay, and that state has to be selected from the given set of environment. That means agent will interact with whom? The environment, and with the help of this environment, the agent will perform an action for a particular given state, okay. So what happens is that whenever an agent performs an action in the given environment in a particular state, one reward will be awarded. So here the reward system will be awarded for that agent. So this reward will be performed by this agent, and this initially for the first state, when it moves from one state to another state, okay, so that is st is one state, and it moves to the next state, that is st plus 1, okay. So as soon as it moves to next state, one reward will be awarded. And what happens in the second step, when it is moving from second step to third step, again the reward will be awarded to that agent, okay. So how it will be awarded? It will be awarded in terms in an environment where the agent works, okay, where the agent operates. And how it will be rewarded? I mean, on what factor? Based on the actions what an agent has been taken in the given step. That means when an agent moves from one state to another state, an action also been provided, along with that a reward will be provided. So here in this way the reinforcement learning cycle will comes based on the reward. What happens, the agent will comes to know that, based on the reward it will come to know that the following step what the agent has been taken, if it is in positive way, that means the reward can be in positive value and it can be negative value. If it is in positive value, the agent think that it is going well, okay, it is going in a, it is going correctly. If the agent goes in a negative direction, if the reward will be in a negative form, so the agent will this kind of cycle will make the agent to take a step where you can maximize the reward overallly when you reach to the final state. So in that sense, this reinforcement learning cycle will perform here. So before actually going to the Markov decision process, first we are seeing the basics that how can you formulate Markov decision process. It is not just directly that I can start directly the Markov decision process, because first we need to understand the basic terminologies what that are being used in Markov decision process. The first one is about the agent. As you people are already aware, we have discussed previously also that what is an agent. The agents are generally as a software programs, okay. Normally, because if you are using a software based AI, if you are using a artificial intelligence technology in a software, that means you are using software program as an agent. So here you need what is the role of agent is that has to take intelligent decisions, okay, and they are the learners. Who are the learners here in reinforcement learning? Agent itself, because based on the reward system only the agent will try to try to rectify, and it will learn from the previous feedback, from the previous what do you say that reward which achieved in the previous states. Based on that only it try to learn it, it try to optimize that. So that is why the agents interact with the environment. How it interacts? By actions, okay. How it interacts? By actions, okay, because the actions because the actions what an agent performs, it will be performed in an environment, and based on that actions it receive rewards. That's the most important thing, okay, based on the actions. The next thing is about environment. Just now I said what is the environment, okay. Wherever whatever the problem that has to be performed, that has to be demonstrated, that has to be solved, it has to be solved in where? Environment. Agent works where? At environment, okay. Agent interacts environment with an action, so the actions will be performed in environment. So that's why you can have real world or simulated environments wherever the agents will interact. So this is kind of environment, that is in environment refers to. Now the next thing is about state. State is something, the position of the agent, something like agent is at one position, okay, at some time the agent changes its positions by performing one action. So it means whenever it changes a position, so what happens is it moves into another state, okay. So moving from one position to another position is called moving from one state to another state, okay. That is how it means for that. And same thing, whenever an agent performs an action, what happens? The environment gives the agent reward, okay. Who will give this reward to an agent? Environment will give the reward, and based on that a new state means new position will be allocated for the agent to perform next coming action in the new state. So in that sense the state performs. Similarly, what happens is what an agent cannot change arbitrarily, that is considered to be part of environment. For example, like an actions that has to be performed by whom? By an agent, okay. So actions actually are decisions. What agents will decide, that decisions will be implemented. Whenever the decisions get implemented, so that will be implemented with the help of whom? The actions, okay. So here the actions will be performed by whom? By an agent. And the state can be anything which can be useful in choosing actions, okay. For at particular position what type of actions you can perform, at one particular position what type of actions you can perform, at one particular state what type of actions you can perform. So the state is responsible for making an agent to choose a particular action, a set of given a set of action, you can select any one of the actions which best suited for you. So what we can assume, we do not assume actually here that everything in the environment is unknown to the agent. Agent knows some of the part and agent doesn't know some of the part. For example, like reward calculation is there. That reward calculation, actually reward will be provided by environment. Just now I said you, the reward will be provided by environment to an agent. So here, so the reward calculation is actually a part of environment. By that we can say. Now even though the agent knows a bit, I mean like the agent know that how this reward will be calculated, okay, but what is happened is that is I mean that state in which they are taken, I mean but still the agent doesn't have any control on that reward, okay. Agent knows about that, but agent doesn't have any control on that, because that control will be taken by environment. Only the agent knows that what can be the reward, I mean what reward can be provided for that. So we can safely say that the agent environment relationship represents the limit of agent control. I mean there is some limit in agent control, that means the agent has some limitations. Agent has some limitations. Even after knowing, even after having a knowledge on the reward system, but still agent can't control that reward system. So that is why the limitations are there in agents with respect to the environment. Now this is how the basics here, but before actually we used to go for Markov decision process, first we need to know Markov property. As I already mentioned just now that we have already discussed the Markov process, first order Markov process, second order Markov process in the previous unit. So still what is Markov process we need to revise here is that, well, you know what transition is, something you are changing from one state to another state is called transition. What is meant by transition probability? I mean if an agent, okay, the probability by which an agent will move from one state to another state. I mean if a agent is there in one state, this is my S1, where an agent is there in S1 state, and if it is moving in S2, okay, the probability by which it moves from S1 to S2 is your transition probability. That means if it is 0.8, let us assume, so now this 0.8 is what the transition probability moving from state S1 to S2, okay. So that is why this is termed to be as transitional probability. Now Markov property is what, you know, Markov already we have discussed that whenever if one particular thing goes from one state to another state, I mean here we are considering agent, so if an agent moves from one state to another state, so it won't concentrate on the previous states. For example, like S1, S2, S3, S4 is there. Now if an agent is moving from S3 to S4, okay, so what happened is that when it moves from S3 to S4, it don't concentrate on the previous state. That means it won't concentrate on S1, it won't concentrate on S2. It will just concentrate on the S3, that means the current state is responsible. That means you can get this statement that future is independent of the past, okay. The future state is S4, so it is independent of the past, means S1 and S2 it doesn't focus on that, it just concentrate on S3, the current state. That is only I said you that is memoryless process. Why memoryless process? Because it doesn't hold the records of the previous states, it just have it will just concentrate on the current state. That is the main role of Markov property. So if I am representing this in mathematical terms, I mean if ST plus 1 is the upcoming state, something like a S4 is there, now it will just concentrate on ST, that is S3, okay, because and here, so you can say that S of t plus 1 actually if you won't consider Markov process, it can have multiple state S1, S2, something like that. Means if I'm moving to S4, then I should concentrate S3, S2, S1 in the normal case. But what does Markov process says? The Markov property says that it just depends on the S3, not on the other states. So that's why f of t denotes the current states and s of t plus 1 denotes the next state. Just now I said you, right? So current state is S3 and future state, I mean s of t plus 1 is S4. So this is how it means that, and s of t to s of t plus 1, it is whenever what is this equation means that the transition from state is entirely independent of the past. So here if you concentrate in this part, what it means that it is not concentrating on the previous states. So you can consider that RHS is equals to a left hand side or equals to right hand side, because it is having because by that we can say that it is Markov property. As you know that current state because already captures the information of the past state, so that is why you can term this RHS is equals to LHS. So this is how about Markov property. Next comes to state transition probability. Like as we have seen what is transitional probability, right? So if I am using state, for example, up to now what we have seen just now is about transition probability. That means if I am moving from one state to another state, I have transition probability, right? So for Markov state, what happens is that if I am going from ST to ST plus 1, that is any other successor state, the state transition probability will be in this way. So ST plus 1 is the new state, future state, which is represented as S dash, and the current state is ST means S here. So if what you can term as S dash, S means the current state, S dash means is the future state. So probability P of this one can be represented in this way. That means, for example, if an agent is there from first state and it is moving to the self state only, that is called as P11. And if the agent is there in the first state and it is moving into the second state, that is P12, so on up to n states. Similarly, if it is in second state and if it wants to move from second to first states, so here it will be what? Second to 1 states will be 2 1. So P of this is 2 2, so on P of 2n, and like that P of n1, n2, so on P of nn. So what I said you that if a state is there, okay, if a state is there and if it wants to go to some other states, okay, this is S1, S2. So overall probability of S moving towards itself or towards other states will give you the value as 1. Like if I take as here 0.4 for self state, so if it is 0.2, that means here it will be again 0.4 only. So 0.4 plus 0.4 plus 0.2, it gives you the value as 1. That means P of 1 1. So for example, this is P of 1 1, this is P of 1 2, and this is P of 1 3. So overallly this value will give as 1 here. Okay. So that's why sum of each row is equal to 1. What is this sum of each row? So this is my row and this row will give you as 1 value. Okay. So in that sense you need to remember. Now this is about state transition probability. Okay. Now next is about Markov process or Markov chains. See, Markov process means memoryless process, memoryless random process. Memoryless random process means here the states on which it is moving from one state to another states are not in sequential order. The states are here random state. That is why Markov process you can call as memoryless random process. Memoryless because it doesn't store the previous record, it is just concentrated on the current state which used to move from current state to next state. And also it is random process means the states by which it the communication happens here is based on the random states. Okay, for example, like if you have S1, S2, S3, S4 is there. Okay, so if I say Markov chain means how I can say I can use generally S3, and S3 it doesn't mean that it has to go to S4, you can go to S1 as well, you can go to S2 also. So there is no specific order here, that's why it is random process. So here S3, S1, S2, and S1 also can go to S2, S1 can also go to S4 as well. So here if it is going here, from S3 you can go to this one. That means when it is going from this S3 to S1, so it won't concentrate on the previous states. Previous states means S1, S2, okay, S2 you can consider. So randomly you can go here, that is all it means. That's why you can term this as Markov chains. What you can call this as Markov chains, or else you can also call as Markov process. Okay, and what you can have is that about transitional probability matrix. Just now we have seen the what is about transitional probability matrix. The same thing you can consider here while you are moving from one state to another states, including the self state. I mean, you can take S of 3 as well, okay, S of 1 also, and S of 2 also. So 2 or 1 or 3 refers to the self state. Here one example here is there already, just now I said you, but still there is one practical example. For example, there are 3 states: sleep is one state, run is one state, and ice cream is one state. Now what is this here is that here you can observe that for a sleep state, the overall probability, that means sleep refers for sleep, okay, in the sleep state only with a probability of 0.2, okay, and when it is sleep and if it wants to run with so it changes the state with the probability of 0.6, and when it is in sleep state and if it wants to change into a next state called ice cream state, so it is changing with the state with a probability of 0.2. That means if you observe from sleep state, overall probability is 1. How? 0.2 plus 0.2 plus 0.6, it will give you as 1. Okay, 0.2 plus 0.2 plus 0.6. So overall it will give you as 1. Similarly, if you see in the run state, if you are in the run state and if you are preferring for running still, that means you will be in a probability of 0.6. But when you want to change with the next state called ice cream state, so the probability will be as 0.3, and when it moves to a next state called sleep state, the probability is less, that is 0.1. So if you see 0.6 plus 0.3 plus 0.1 will give you again as 1 only. Same thing happens as well for ice cream state also. So in this way what happens is that you can take Markov chains here, okay, and you all of this you can represent through what? You can represent through state transitional probability matrix. So here these are what the samples, that means how it is moving: sleep, run, ice cream, again sleep. It doesn't mean that when you have taken sleep already you cannot move to a same state again. So you can go after going from ice cream to sleep. So something like a chain is there. Chain is how the connection has to be performed. It can be something which is repeating to the same state again, that can also happen as well, because your repetition is there. For example, in the second sequence, second sample, you can observe that ice cream, again it is preferring for ice cream only, then it is preferring for, so there is no sequence at all. That the process is completely random in nature. But what has happened here is that when it goes from one state to the next state, when it is so the next state is just depends on the current state. That means the run state is just depend on the sleep state, whereas the ice cream state is depend on the run state only, and whereas the sleep state is depend on the ice cream state. It is not depend on the previous states. Similarly, here in the second sequence sample, the ice cream state is depend on the sleep state. Again the ice cream is again self depend on the same state, and the run state is depend on the ice cream state. So in that sense this Markov chains are to be used. Now this is how a Markov process, that it is called a random set of sequences. What you can term this as random set of sequences. Now the thing is that we have seen just now about Markov chains, but as we are concentrating on what? We are concentrating on Markov decision process. So Markov decision process is just not Markov chains, but still here one thing is also included in that. What is the thing is that it includes reward system. Just now I said you in reinforcement learning it is feedback based system. So feedback means reward based system. So here the rewards been allocated, okay, from moving from one state to another state. But Markov chain is something where we are not using reward system. But here here we are going now in reward system. So rewards are actually basically a numerical values. Who will receive this rewards? Agent receives. Who will give that reward? Environment will give the reward. Okay. Okay. For why it will give you the reward? Because you are performing some actions at some state. Based on the action what you have preferred from the from one state, what happens? The reward, the associated numerical value will be given by the environment. And I said you just now that before that only initially I said you that the rewards can be positive or negative. How it can be decided that it is positive or negative? It is based on the actions of the agents. Because I said you, whenever an agent is there in one particular state, based on that state there are multiple actions has to be adopted by an agent. Okay. So that actions, based on that actions, what happens? The value, I mean the reward value will be get decided, and who will provide that? Environment. So that is why in reinforcement learning what has happened is that what is the main purpose of reinforcement learning is that we need to maximize the cumulative reward. Cumulative reward means, for example, if an agent moves from one state to another state, so on up to moving from different states, so it is moving something around 5 to 6 states. So cumulative reward means when it moves from 5 to 6 states, so 5 or 6 times the rewards will come. So if you include all of these rewards, so cumulatively whatever the reward you will get, so that reward we have to maximize that reward, and for that we need to adopt the strategies that how can you maximize the reward. So that is what our intention is for. So that is why the total sum of rewards the agent receive is called as returns. Okay. What you can call, for example, if you see r of t plus 1 means it is the reward you will get when you are moving from a state t to t plus 1. When it is r of t plus 2 means you are getting, I mean the agent gets a reward when it is moving from state t plus 1 to t plus 2, and so on. What happens? It gets a reward at the tth state, I mean for the final one. So if you combine all of this one, what do you can term this as returns? So simply returns are what? Cumulative values of all the rewards which an agent gets from the initial states to the final states. Final state. So this is how the return is there. The next thing is about Markov reward process. Now we have seen regarding rewards, okay, and we have seen about returns. Now this reward we are implementing in Markov process. So how we are going to implement is that, as we have already seen what is Markov chain. Markov chain is something, what is that? It's a random process, okay, random process moving from one state to another state, which is a memoryless process. That is how the Markov chain, right? So now we are implementing this Markov chain in reward process. So how we are doing? We are using a set of states, because in Markov chain what happens? A group of states will be there, and you know in that Markov chain we have probability matrix as well. So using that states and transition probability, what we are doing is that we are implementing the reward system into that process. So here just now I said you the reinforcement learning is to maximize the rewards. So that means we need to add the reward in Markov chain. So if you add the reward in Markov chain, it becomes as Markov reward process. Simply Markov chain plus reward is termed as Markov reward process. So Markov decision process are the Markov chains. Simply what you can say that Markov decision process are the Markov chains with values judgment. I mean values judgment means whenever you are going to one value, values judgment is your reward. Value judgment is your reward. So we get a value from every state, our agent is in that way. So how can you mathematically define the reward process is here? You know, this is how something a reward process. So R represents for reward process, and what happens? You will get a reward R of t plus 1 for a particular state, that means state ST. Okay. So in that way the reward process will be defined mathematically. Now, so what this reward here, if you see RS, just now I given you this RS. So this is how much reward we get from a particular state ST. So it's just a value. It's just a value, numerical value. Just now I said you the reward value will be what? A numerical value. So you will get for a particular state what reward value you are getting, okay, for a particular state st. So this tells us the immediate reward from that particular state our agent is in. So what is this? Actually our immediate reward. So what is our goal? The goal is to maximize these rewards from each state, not only overall. If you maximize the reward from each state, overall if you club all of this rewards value, so the the return will be in maximum number. So that means, that's why I said maximizing the cumulative reward we should get from each state. Now the next thing is, the main thing is what we are discussing just now is a Markov decision process. So what is this Markov decision process? For example, if you are taking a decision problem means a problem where an agent has to decide what state has to be going to be get selected. But we are taking in an environment which is fully observable. Fully observable means the agent knows completely about the environment, okay. And stochastic environment means here the agent doesn't know how to move from one state to another state, okay. The states are not deterministic in nature, so that's why the environment is stochastic environment. And what we are doing in this environment, we are using Markovian transition model. Markovian, just now we have seen that how this Markovian transition model means, it is using Markov process in that, and in that Markov process we are adding still reward. So something Markov decision process means we are taking, see, Markov MDE refers to, we are taking an environment which is fully observable, which is stochastic environment, okay, by using Markovian transition model, and at the same time we are using reward system. So all together will forms to as Markov decision process. So all of this together what to be performed as Markov decision process. So in that one, simply if I define Markov decision process, I can say that it is a set of states, a group of states, because an agent has to perform from one state to another state. That means number of states will be there, so you can form them as set of states, and the initial state you can term as S0, which is called as the initial state, and a set of actions. Why actions? Because if I move from one state to another state, I have to perform some action. So as you know, there are multiple set of states are there, so multiple set of actions has to be performed. So that is also included. And transition model also we have seen that how can you move from one state to another state. So here this first S represents the future state, and this S represents for the current state. So the future state is depend on the current state only by performing with an action called A, okay. That is how the transition model refers to. And also the finally is that we are using reward system. So reward function is there, which is termed as R of S, okay. And also one more thing is that here, as you know, the environment is stochastic environment. That means the environment doesn't that means the agent doesn't know how to move from one state to another state. I mean, which state will give you the best path in order to reach to the destination. So for that there we require one kind of solution. I mean, we require some kind of rules that has to be adopted by an agent in order to go to the destination state. So the solution of that Markov decision process is called as policy, okay. So that means it also contains a policy. What this policy refers to? Policy is actually a solution to the Markov decision process. I mean, this policy will be useful in order to map, if I map a state S to an action, so indicate that what state has to be chosen, what best state has to be chosen for the next step. So that's why this policy has to be defined in Markov decision process, because this is actually your solution, okay. So this policy will be denoted by pi, okay, denoted by this phi, and this phi of S is actually what? An action. Is the action recommended by policy pi for a state S, okay. So now if you take this example, for example we are taking a grid world example, okay. Here for example, this is 4 by 3 environment is there. Okay, for example, you consider this as one room, this is also so that means totally how many rooms are there? 12 rooms are there. The agent is initially at this room number 11. 11 refers to what? This, I mean, this is your 11, which is the agent is currently there. Now what happens is that this is the closed room, okay, where 22 is what? The closed room. That means agent cannot enter to that room because it has been covered with a wall, thick wall. Okay, so this is how something closed room. Now what happens is that if an agent reaches to the room number 43, okay, so the agent will be awarded with a reward value called +1. And if an agent reaches to a state called 42, I mean reaches to state, you can say, you can consider as room of called with a value called 42, the agent will be rewarded with a value called -1. So what our reinforcement learning, what this Markov decision process is to maximize what? The reward. So for maximizing the reward, the agent shouldn't enter to this room, I mean to this state, okay, because the reward will become simply as -1. Okay, but our intention is to maximize what? Maximize the reward value. So we need to find the best solution in order to reach to this state. Okay, so that is why. So what happens is that just now I said you, so there are 4 directions, I mean 4 actions are there. What are the 4 actions you can perform? I mean agent can perform. The agent can perform either it can go in up direction, down direction, either in left direction, either in right direction. Okay, so these are what the 4 actions what an agent can perform here. Okay, so here because as it is 4 by 2 is -1, so agent should avoid this state. Okay, so agent should avoid this state. So what is going to happen is that the move, whenever an agent moves from one state to another state, 80% of the time the intended action works correctly. But I mean normally it gets corrected, but there is a chance that 20% of the time the action agent takes causes it to move right angles. Right angles means here if an agent moves to either in right direction or either in left direction, it is called as right angles. What this is called as right angles. So the probability, that means the amount of time it can take 20% also if it moves in right angle. So if right angle, that's why we divided into half of that. So what is you can take, if you take in probability, so 80% of time it moves in forward up direction means, so the value is 0.8, but for right angles the value is 20% here in this line. 20% of the time the action agent takes causes it to move to right angles. Okay, so 20% right angles means as it can be in both the direction left and right, so we divide it equally, that's why we taken as 0.1 and 0.1. So what is going, if you observe this one here it is stochastic environment means the agent doesn't knows, okay, by which path you can reach, I mean the agent can reach to the final destination. So here in every state it has to observe that if you go to this direction, what is going to happen, what reward you will get, because I said you moving from one state to another state will give you a reward. So that is why what happens is that if an agent moves to this state, it will be rewarded as +1, and if an agent moves to this state, at this state, I mean that agent has to actually avoid, so -1. But other than that, all the other states have a reward of -0.04. So in that sense the agent has to decide that which state should be best suited, which direction should be best suited. So if you observe this carefully, what you can find is that, okay, so there are 2 sequences actually. What are these 2 sequences here is that right, right, up, up, right. So if you go this one, what is the way? This is right, again this is right, okay, then up, then up, then again right. So here it is moving to the destination. Then what is the another one? This up, again this up, and this it is moving to right, again from here it is moving to right, and finally again it is moving to right. So what are this? These are what? The two sequences you can find which is the shortest sequence. Okay, we know, I mean, but the agent is how something works in a stochastic environment. So agent has to consider this. The agent has to try for each and every state. So for example, if an agent took this second one, okay, for the subsequent, so whatever we are just taking one example here. If you take this second sequence, what is going to happen? Just now I said you 80% of the time and 20% of the time will be wasted. It will be taken actually by right angle. So if the agent says up, the probability of going up is 0.8, where the probability of going left is 0.1. Thus now I said right angles means left direction 0.1, right direction 0.1, and the probability of going right is 0.1. Okay, so in that sense what happens? The agent has to perform. So ultimately what we can say is that the agent receives reward each time step. Okay, so what happens? The initially if I am going to from one state to another state, small rewards will be given. Okay, but when it goes to the final reward, big rewards is where? Big rewards will be at these states. Big rewards will be at this state, that is here. If directly it goes here, +1 will be provided here. When it goes directly, it will given as -1. But other than this states, small rewards will be given, such as we consider the value as -0.04. So in that sense what is going to happen is that every time the agent has to learn here. So because of that, so generally what happened, the short sequencing is in a desirable way it is accepted, but the agent has to perform. So we should think in the way where we are using a concept called optimal policy. Okay, optimal policy. What is optimal policy means? Just now I said you that policy. What is policy? We refers to what the policy is, the solution to the Markov decision. Policy means how you are reaching, how an agent reaches to that state. That is how the policy. But optimal policy here, optimal policy means whenever a policy is executed starting from the initial state, the stochastic nature of the environment may lead to different environment history. Stochastic means we can't say that agent will move to this path only as we have recommended, because agent will be in stochastic environment. So agent can move either in this direction, either in this direction, either in that direction. In every direction can move, but agent can't move to this path, and agent has to avoid this path. Agent has to avoid this path. So in that sense what happens is that we are using optimal policy. So the quality of policy is therefore measured. Okay, how best suited the agent is performing the actions, and it is changing from one state to another state. So is therefore measured by the expected utility. Utility means how best it can perform in order to increase the performance of the agent. Okay, in order to increase the so that is called the utility here. So expected utility, possible environment histories, okay, environment generated by that policy. So based on that also you can perform. So here optimal policy simply is a highest expected utility. Highest expected means highest reward system should be provided. Just now I said you that reinforcement learning is something where what the thing is that it has to maximize the cumulative reward. What is this reinforcement learning? It has to maximize the cumulative reward. Overall reward should be maximized. So for that purpose what we are using a policy called as optimal policy, which is giving highest expected utility. So for that purpose what we are denoting pi star, which denotes for optimal policy. So here the agent decides what to do by consulting its current percept. Okay, by current state, which tells it in the current state and then execute the action based on. So this action is similarly in a normal policy, how this action will be in this way, but when I am using optimal policy, the actions will be taken with the help of star in that one. So if you observe this example, so if you observe the graph figure A, what is going to happen is that, like we have said you that if 0.04 is what the reward will be given from moving from one state to another state. Okay. For example, if an agent is in this state, let us, if the agent is in this state, that is in this state, what happens? The agent should simply, what happens, should avoid this path -1, because at the right direction there is no way, and if it is goes to up, what happens, directly it has to avoid this state. So the agent should move to this state only. Okay. And next is, if the agent is in this state, the agent can move either to in this state or either into this state. Okay. And if, for example, if the agent is in the second 2-1, if the agent is in 2-1, what is going to happen? The agent can move either, the agent we should move to this direction, because if you go, this is the wall here. So wall means the agent can't move to this one. So agent will move to this one. And if the agent is in this state, the agent will move to this state in up direction. And okay, and here if the agent is in, what happens in the state 2, 1, 2, okay. So here the agent should not move into the right direction because there is a wall here. So agent will move to the up direction. And when it is in this state, what happens, the agent should move to in the right direction only, okay, because there is no other way. And if the agent is in the direction, the agent can't move to this path because there is a wall here. So agent has to move in this direction only. And if the agent is there here, so what happens, the agent will move to this direction, because by this the agent can achieve the destination, that is the final state, terminal state. So in this way optimal policy will be decided. But for example, if there are different ranges are there, okay, for in the figure A we just have this value minus of 0.04, but if there are different ranges are there, suppose here in this diagram the range is that the reward of the given state, if it is less than minus 1.6284, so what is going to happen is that the agent, because if you are moving to this, if an agent moves to one state to another state, the reward can be less than, it is equal to also, okay, less than or equal to minus 1.624. So still this, if the agent is in this position, it tries, it accept this state, it accept this state, because it is -1, right, -1, and -1, what, -1 is good compared to minus 1.6284, okay. So that's why it will take the risk here to enter into this state, because the ultimate goal is to increase the reward value. The ultimate goal is to increase the reward value. So because of that, what is going to happen is that the agent will prefer here. But if you take in this example, the agent is moving towards in left direction, but here, because what is going to happen is, as the reward value, the range has been changed, that is, it is less than or equal to minus 1.6284, that means minus 1.6284 have more negative value compared to -1. So it prefers to enter into this state, because -1 is less compared to minus 1.6284. That's why it takes the risk to enter into this state, because ultimate goal is to reach, ultimate goal is to decrease the reward value, to increase the reward value. So for that purpose it will be taken. So that is why here what this optimal policy will take, recommends that it takes the long way round. Generally we have chosen the short way, but that is not the case always. So it may choose the long way round rather than taking the shortcut, and it allows it will take risk by entering 4 by 2. In this state also it enters. Okay, 4 by 2 means this state. So it is taking the risk to enter into this state also, because here what happens, the reward value, that means the reward value is higher than this one. Okay, here actually it is minus 1.6284 and here it is minus 1. So that's why it prefers to enter into the risk state. That means every time, based on the situation, the balancing of risk and reward will be performed, and the changes will depend on the value of R of S. Okay, so because of this R of S, the balancing of risk, okay, and reward will be balanced accordingly. Okay, so R of S is a very important value. Based on that only the things will be considered here. That's why I said you this is the first case. So even it is so painful that, but still it prefers to go, the agent heads to the nearest exit even if the exit is worth minus 1. So here it will exits by entering into this state minus 1, because this is lesser the value compared to this value. But when it goes to the next range, what is the next range? The next range, the range is less here. So now if you observe in this state, as the reward value is in between minus 0.4872 and minus 0.0850, so here the reward value is increasing. The reward value is increasing. That means what happens is that because of that, now if an agent is in this state, so it won't go to this state. Rather than what is going to happen, if you refer this point, you will come to know that the agent takes the shortest route to the plus 1 state. Based on what? Based on this value, and it is what happened, and it is willing to risk falling into the minus 1. So it won't concentrate to reach to this state. Simply if the agent is there in this state, so it will try to reduces the path, so it will go from here, here and here, finally it goes to this state. And if an agent is there here, it goes to this state. So in that way what is going to happen is it will reduces the path here, because the risk is reduces here. Next, if you go in the third way, something the risk is very less. Okay, the risk is very less because the reward value is in between 0 to 0.021, minus of 0.021 to 0. That means the reward value is approximately near to 0. So here you can find that the optimal policy will decide that there is no risk at all. Okay, there is no risk at all. So what happens if you observe this 4, 1 and 3, 2, the agent heads directly away from the minus 1 state. Okay, 4, 1 means this state. Here in this state and in this state, what happens? It it avoids to enter into this state. Here there is no path, but still it prefers this way because there is no risk at all. So why should an agent should enter into this state? So because the reward is more here. So that's why it will avoid minus 1, because if directly an agent enters into this state, it will get the value as minus 1. So that's why it avoids minus 1 from both the ends. Here still it is wall is there. Here it is still wall is there, but still it tries to move on to this state because the agent knows that it will, if it goes to this, it gets minus 1. That means when it comes to the current state, then only it will determine the future state here. Okay, it won't know the it won't takes the conditions of the previous state. So here when it comes to this state, so it knows that if it enters into the next state, So it will be -1, so it avoids entering into the state. So it focus on this state because it is wall, but still it tries to avoid to enter these states, okay, in that way. So after that it can go in any other direction, but it avoids to enter into this state. But if in the fourth case, finally what is going to happen is that, as you know, the reward is greater than 0. As the reward is greater than 0, moving from one state to another state, so simply it won't ultimately go to this state. Also it will avoid to enter into this state, because you know ultimately here only the reward is getting 0, it is getting greater than 0. So greater than 0 means it can be any value. So in this step you can come to know that if the reward is moving from one state to another state is greater than 0, that means it can be any value. So that means the agents avoids both exits, because you know normally only the agent for this reward value is getting 0, greater than 0. So that's why it avoids both the exits. So here that's why it is neither entering into the +1 nor it is entering into the -1 state, okay. So in that sense it happens. So what is the main thing is that of Markov decision process is what is the main important thing in the Markov decision process is the balancing of the risk and reward is more important here. If there is no risk, like in the last state there is no risk at all, there is reward only, so it tries to avoid that path where the problem arises. So, and that does not arise in deterministic search problem. So this actually doesn't arise in deterministic search problem, because in deterministic search problems the agent knows what will be the current state, how the current states are, how will be the next states. But this is how something where if you go in stochastic search problems, the problem arises. So at that time this MDP, I mean like Markov decision process will be used, okay. So because of that reason, not only in AI, it will be used in OR, economics and control theory, the same concept, okay. So with this I have completed this session, okay. So in the next session we'll be seeing regarding utility theories and the basics on utility. So with this I conclude this class. Thank you.